non-standard time. We were fortunately able to work this out so that Daniel Keefe from the University of Minnesota could come join us for the day. And I've known Daniel for a number of years and recently visited him at the University of Minnesota and saw all the really cool work that he was doing there. So I wanted to invite him out so he could share some of that amazing work with us. Daniel, please join us and tell us about your research.
Thank you. Thanks so much, Chris, for a great introduction. I'm really happy to be here, so thank you for inviting me too. There's already been some great conversations, and I think there's more to come. So I thought I'd talk to you today about working in virtual spaces, and the emphasis is kind of on the working. I want to tell you a little bit more about what that means to me. In a nutshell, it's this idea that you're not just working with visuals, but you're really also interacting with those visuals and thinking of visualization as a real exploratory process. So let me tell you a little bit more. I thought actually before getting into some technical details, I'd start with a slight tangent. And I have a background in art. And so one of the things that actually is quite motivating to me is to think about how artists work and how some of those same processes can come into the visualization processes we use and also the tools that we use. So this is a piece of vine charcoal. And I'd like to show this picture for a couple of reasons. One is that, just in 30 seconds with this piece of charcoal, you can make 5 or 6 marks and then maybe smudge them with their hand. All have incredible variation. Okay? And that comes from the physicality of it, how you hold this thing, the pressure you exert, how it interacts with the paper. So it's actually very, very rich. Yet it's probably the simplest tool you can come up with. I mean, this is a burnt piece of wood. Okay, so very simple, yet incredible richness to what you can create with it. Here's a couple drawings I did at one point, and they're just, it's just a matter of moving this stick across the paper. You get very rich interaction in terms of what you can do with it, but then also the visuals you can create can be very expressive. So to me, actually, charcoal is very inspiring. What I want to do today is sort of go from that to some of the scientific applications we're working on in my group. And we just redid our webpage, so I had to get a picture of it in here. And I thought I'd just use this to highlight a couple of the application areas for the work that we're doing. Some of them I'll talk to you about today, and some of them I'll just use as a little bit of introduction here and now. First is visualizing motion. And when I say motion, I mean the kinds of rigid body mechanics you'd find in, say, biomechanics, orthopedists studying how the human neck works, okay, and things like that. And there's incredible ability today to collect really high-resolution data that are really time-varying. The essence of the data is motion. And scientists are really excited about this, but like so many other disciplines, they really don't know how to work with the data. So I want to talk to you about some of the work we've been doing there. Just some other things we're working on. One is a interactive visualization that's hooked up to a second harmonic generation microscope. Okay, so how do you sort of stream data from that into a 3D environment and close the loop where instead of this taking a long process to sort of get your data, then realize, oops, we should have changed the imaging a little bit, to make that a very tight, iterative process where you get some insight from the data immediately and then can use that to inform future data collections. A couple other things, I just want to give you a sense of some of the breadth of things we're thinking about. This is a new project we just started with a collaborator in the Writing Studies department, and he's studying ancient Greek oratory. So people who gave speeches to a group of 10,000 citizens and try to sort of convince them, oh, it's time to go to war. The really interesting thing is that this is all happening not in the sort of temples and theaters and the places that have been really well preserved, but in buildings that were really sort of everyday meeting houses. And so they were built of wood, and there's not much remaining. So a lot of the reconstruction of those is hypothesized. The other interesting thing is that these researchers are really interested in sound. Okay, how did the auditory experience, what did that look like in these spaces? And it's so fun, there's actually evidence in some of these ancient texts that just like today in your crowd of 10,000, wasn't just everyone sitting there placidly, but you've got your group of hecklers over to one side and so on and so forth. So we're thinking about how do you model that, and how do you sort of recreate this experience, and how do you use that to inform reconstructions of the space. Okay. Another project I'll talk a little bit about today is data-driven surgical training. So surgeons who are learning how to perform minimally invasive surgeries. And again, there's new ability to collect data. So we can learn about how surgeons are manipulating tools in three-dimensional space, what forces they're using, and so on, through optical capture and also mechanical devices that are just becoming available now. But again, the question is, well, what do you do with this data? So I'll show you some of the things we're working on. Okay, so the purpose of sort of showing some of that breadth is to kind of motivate where I like to do research, and that's really in the center of this diagram. So a place where you have both a problem in picturing data for understanding, but then also in interacting with those pictures. Okay, so the visualization really becomes a process, and it's an exploratory one, where it's really trying to dig into the data to find new insight. Okay. So I think many of the projects that I just described actually really have this flavor. I'll show you some more details today, but one of the fun things for me, again, is I think charcoal's there too. This is sort of where the space where drawing lives. And so this is sort of a motivating statement for me. What I'd really like to do is make computational tools for science, engineering, creative design, these types of applications that can be as immediate and powerful and effective as drawing. And I don't know, depending on your background, you may also find this inspirational, or you may say, oh, hey, I just bought this $1 million computer, and you're telling me a piece of chalk is more powerful. So I don't know, you can take it or leave it, but for me, this is actually really motivating when I'm thinking about how immediate it is just to draw. And can our tools reach that level of expression, not only in the interaction, but also in the visuals you can create with them. Okay, so to talk about some of those points today, what I want to do is touch on three kind of research thrusts in my group right now, the following. And within that, I'll kind of skip around to a couple different projects, but I think these are sort of three main areas in which my group's working right now, so I'll give you a little taste of some of these. The first is visualizing motion. So biomechanics, for example, as I mentioned before. So why is this interesting? I was talking earlier today. This is like one of those times like when you first learn physics and then you go out and you look at the world and you realize like you look at everything differently. I think when I started thinking about motion in this way, all of a sudden I see it everywhere. But I think it's really true, actually. Almost everything we study has a component of motion to it. So I really like this quote by Murray: from the invisible atom to the celestial body lost in space, everything is movement. Okay, it's the most apparent characteristic of life. It manifests itself in all functions. It's even the essence of several of them. So I think the study of motion, so how do we depict motion, is actually really fundamental. Of course, Ray and Mybridge did some excellent work pioneering this, and their photographs, even today, really provide a lot of inspiration to visualization methods. I also like this guy in particular because I think he looks like one of the knights who say "knee" in Monty Python. Okay, but it turns out there's some really interesting contemporary applications of trying to understand motion. So I will touch on all of these today, actually. This is what I was just mentioning to you a minute ago, the ability for surgeons in training to actually sort of capture their motions. And this is device that's now being manufactured by Simulab. It was a spin-off from the University of Washington, which has an interface that's the same as laparoscopic tools, but has mechanical sensors on it, so you can understand where those tools are moving in three-dimensional space and what forces are being applied by the surgeon and so on. So between this and surgical simulators, optical motion capture, there's great potential now to collect data, even on really intricate movements like what a surgeon would do. Another application that's really quite interesting is working with orthopedists. So one of my closest collaborators is David Nuckley at the University of Minnesota. And he studies the human spine, both in children and in adults. So thinking about how the movement of that spine works and how that changes under different situations, like as children grow up or as you have different diseases or disc degeneration or operations and so on. And then a third application area is actually really quite similar, but it just has to do with animals rather than humans. And this is some work I started when I was a graduate student postdoc at Brown University. There's a great group there of evolutionary biologists and also some orthopedists who study really fascinating and kind of wacky from the outside motions. So one of them is how bats fly. They actually fly bats in wind tunnels. Another, which I'll talk a little bit about today, is how pigs chew. That turns out to be an interesting chewing pattern. Ducks, actually, maybe even more interesting than the pigs. So the mechanism of the bill moving, for example, is really interesting. And so on and so forth. They've got all sorts of wacky animals that are a lot of fun to study. But all of these have this problem of sort of trying to understand data that fundamentally describe motion, but where that motion is really complex, and it's complex in both space and time. So some of the imaging techniques used here can capture motion at 500 hertz with sub-millimeter accuracy for the internal motions of the bones. So this is the kind of thing where 5 years ago the scientists would have said, "Oh, I can't even dream about what I'd do if I had these data." But now they're really faced with this challenge where they have the data, but quite often it's only 2% of it that they actually use when they sit down and write their paper. There's this sense of, oh, we've got this three-dimensional data, we really need to take advantage of it. It's so exciting, but we don't have the tools to know how to do that. So that's where we're trying to step in. Here's how some of that data is collected, and I know some of you have seen me talk about pigs before, so I'm running the risk of being known as the pig guy. But this was actually one of the first data sets collected using this technique at Brown University. It's a biplane fluoroscopy system, which means it's taking basically X-ray videos from two orthogonal angles. So you get two X-ray movies, and in a separate process you can take a CT scan to get the three-dimensional shape of the bones. And then you can do some computer vision basically to register the two data sources, and you end up with a 3D model of the bones in motion. That's very, very accurate. Of course, the reason why you do this is you can't get a CT machine to run fast enough to capture this type of motion. So a bit of a process to collect the data, but then you get these really interesting motions. This is sort of a starting point for what I'll describe next. This is some older work, but I wanted to just give you an introduction of the type of data we're looking at. So it turns out that this is actually quite an interesting motion to study. It's called bilateral chewing, and you can actually see a characteristic pattern of it. The jaw kind of comes up, goes over to the right, and then down, up to the left and down. And it just keeps alternating. So it's actually pretty rare, and the biologists are interested in understanding sort of how this motion evolved over time. What does it mean in terms of the way the TMJ is working, and how does the morphology, the shape of the bones relate to the motion? Okay, if you can understand that mapping, then you can start hypothesizing about similar mappings that might have existed in animals that are now extinct. Okay, but that was slowed way down. This is actually real time, and this is the first bit of scientific evidence that the expression "you're eating like a pig" really has some truth behind it. Okay, so it turns out to be a very interesting motion to sort of analyze. And how would you go about doing this? Well, just to kind of start at a very basic level, if you just looked at, say, the motion of the jaw relative to the skull, that's the motion of a rigid body in space. So you've got a translation and a rotation about or along the x, y, and z axes. Okay, so these are sort of the types of plots you could extract. Now, even with this, you've got to there's options, right? So you need to pick, where's my reference point? Okay, motion's always relative to something. So defining that, sometimes there's a good anatomical landmark to do that, and sometimes there's not. That becomes very difficult to interpret. So I want to show you one thing that we did to overcome that. It's using a different construct to understand the motion. It's called an instantaneous helical axis. So this is not a new idea. It's been used many times before in analysis, but it's actually quite interesting. Basically, it talks about the movement of a rigid body in space as a combination of a rotation and a translation along a specific axis in space. So the way I like to think of it is foosball. So if your bone is this player, you can move along this axis or rotate about it, and you're describing his movement entirely based upon that axis then. Now the trick comes in, of course, if the axis doesn't pass straight through the bone, you may sort of observe a motion where this axis that you calculate doesn't pass directly through the bone. In this case, we'd see something like a movement out of the page and about this axis. Okay. But it's an interesting construct to sort of think about 3D motions. It's neat because in a single axis you've included all these rigid body motion parameters. There's often a direct visual interpretation. I'll show you some examples of that. And with these new data collection technologies, there's an ability now to look at something that's really an approximation of an instantaneous axis of motion. So if you think of each time step as you move through time, there's sort of a different instantaneous axis that a bone or some other body would rotate about. And that's something that hasn't been looked at very much before, so we became interested in that. Okay, so just a couple examples applied to this problem. Here's a situation, we're looking at the back of the skull of the pig here, and the jaw is just beginning, or is in the process of opening. And so an axis that we calculate for that point in time has a horizontal orientation. Okay, it makes sense to the jawbone sort of rotating about that horizontal axis. If you look at a later step in the motion, we come to that side-by-side aspect of sort of the grinding pattern in the motion. And here the axis has a roughly vertical orientation, which indicates that it's moving side to side. And there's some different data encoded here, so we spent some time designing that particular representation, but I won't go into those details right now. Here's a system that's sort of put together with this idea in place, and you can see, now one thing I want you to notice actually is, even in this horizontal stage, the axis passes through the jaw, not up where not up in the temporomandibular joint where the actual joint is, it's lower. And that actually turns out to be an important indicator because what it's telling us is basically some sliding action happening in that temporomandibular joint. You can see how that sort of, if you put a number of these together, you end up with sort of a surface, which becomes sort of an interesting construct. Let me back up for a second. I want to just make one point. So one of the things that's interesting, if you actually observe the data, you'll notice that up in this joint, the same as in humans, there's a sliding action. So it's not just a perfect hinge. In that case, we'd expect the axis of rotation to go right through the joint, but it actually opens and slides. And just that simple motion is actually pretty difficult to explain through traditional means, in the sense that, I mean, how would you describe that as a biologist? Okay, look, there's a rotational component, but then we also have to define an axis here relative to the skull, and we're going to get X amount of translation along that axis. Even that becomes sort of difficult to reason about as a 3D motion. But instead what you can do is say, look, take this helical axis, and we're just going to think of this jaw opening motion as essentially a rotation. But the key is to think about which axis that rotation happens about. If it happens about this axis, then there's automatically some sliding that goes on in the joint area. Okay. So just that sort of change of how you're looking at the data actually can lead to a more intuitive understanding of the motion. Okay, so all this is sort of a starting point for the kinds of things we're looking at now. And I wanted to sort of present this to you just to sort of make the point that there's some nice qualities to that type of visualization, but I think really the challenging thing is how do we move beyond this type of 3D visualization. So seeing one motion, for example, in 3D, this is great. You know, there's some really nice things. The 2D analysis of the data they're too limited when you're working with such complex data. We haven't seen before, so there is some potential for new insight here. And certainly there's a wow factor that the scientists we're working with like. But the question I really want to ask is how do we move beyond this to support real work, real workflows? And across all those applications I mentioned earlier, I think the common thread that we keep observing is that there's a need to compare. Okay? I think, you know, to this point in visualization, we've often said, you know, creating a single 3D picture is just hard enough. You know, thank goodness I got this. But then if you go back and sort of say, well, what are people really trying to do? Okay, it gets into this idea of like making comparisons among different data sets. So even in the pig case, we're not looking at one pig, you're looking at, you know, a whole selection of them, different, showing different foods and all sorts of things. So you end up with a sense of comparison. And studying spinal mechanics, it's really the case. You do a study there with 200 subjects, okay, and some of them have differing degrees of disc degeneration and so on. So you want to make those comparisons across the space as a whole. So we're starting to go in this direction now. I think this is actually one of the most interesting challenges that we face. Here's one example, and I want to show you a couple more. So this is, again, looking at that pig chewing data. What we've done is taken several dimensions of the data. I don't know, maybe 15 different quantities that are present in the data, like how close the teeth are to each other, the velocity of the rotation, and so on and so forth. So these really are multidimensional data. Then we've done a data dimensionality reduction step, okay, to sort of try to tease out within each frame of the data set which motions are similar and which motions are different. And what we end up with is a series of plots. Now this is sort of showing one line across the screen. Time goes this way. And there's one line for each chewing cycle in this data set. So I don't know, maybe we analyze 100 or so of these cycles. And we're sort of looking for what are the differences in commonalities. And in this case, when we go through this processing step, we can sort of figure out, look, these lines map down here. And we've got sort of another cluster that maps up here. And there's something in the middle. And what we're now trying to do is basically say, these motions, at least for this period of time, are very similar. Okay, so you sort of cluster those together. These ones are very similar. And if I show you a representative motion from each of those sets, then more or less you get a sense of what's in your data set. Okay? So we're trying to sort of follow these rules of do some automated data processing and then combining that with visuals. And the fundamental problem is that there's just too much data. You can't possibly look at all the visuals. So how do you pick the right visuals to show to the scientists? So here we're sort of saying, look, I've got 30, 50 motions, however many this is. If I showed you all of them, you wouldn't be able to do any analysis. It would be too much. But if I could show you a representative set, then you really get some flavor for what's here, and you can begin diving down later into the details. Okay, so that's one example. I think there's many approaches here that could be taken, but the commonality really is like, can you get away from this mindset of sort of showing one at a time and get to the point where you're really looking at a collection? Okay, so I've introduced this realm a little bit. Laparoscopic surgery. I actually tried some of the virtual reality trainers for this, and I was completely miserable. This is like really, really hard to do. So I understand the need for better training tools here. It turns out there's a series of tasks, there's 5 tasks that are called the fundamentals of laparoscopic surgery. And here's a picture of one of them. Now this is sort of zoomed in, so you're just looking at the tools. And this task is called the block transfer task. So you reach in, you pick up a block with one hand, pass to the other, and then put it down. Okay, and there's a series of other, these are just created to like be low cost and cheap. Another one is like suturing a rubber glove together. Basically, you have to pass all these tests without making any mistakes and under a certain time limit to sort of continue on in your studies. So here's a series of them. They're performed using that data capture technology. It's actually called the EDGE system. And basically, you're working with like 2 alligator clips on the ends of long sticks. Really difficult to control. Okay, but this is the type of motion that that we see. And the challenge is, can you analyze this? One of the first things you'd want to do is figure out, is there something that distinguishes an expert from a novice? Okay. And if so, then the next step is, well, can you then feed that back into training mechanisms? Okay, so you could actually develop some like real-time trainers that help you, you know, make a smoother motion straight to a target or something like this. Okay, but we've never seen this data before, so actually we don't know what we should be trying to train people to do. And surgeons can sometimes, just by looking, kind of pick out an expert, but doing that across a large database doesn't scale very well. So I mean, here's a challenge. See if you can kind of figure out here, just with 9 shown, which one of these surgeons is the most expert.
Lower right.
Lower right? I'm not even sure if I know the answer to that. The lower right looks pretty good. Okay, so you can sometimes kind of see qualitatively that something's going on, but sort of to discover what is it quantitatively in the data that makes this person more expert, and can we quantify that? I didn't even make the cut. I'm like nowhere near. I'm like somewhere, I don't know. Okay, but there's 9 of these, and it turns out this database keeps growing like every other. At this point, the application I'm going to show you in a minute, we're just looking at this one block transfer task. Even in this fundamentals of laparoscopic surgery, there are 5 tasks. Okay, and of course, there's many more advanced tasks you might like to look at as well. We're working with data right now that has 104 trials. You know, so you end up with this many frames of data at 30 hertz. It'll take you about 4 hours to watch all the motion together. And you've got about 12 variables per frame and so on. So the database quickly grows, and if you start thinking about the future of robotic surgery, for example, this type of data is going to be available, widely available, okay? Or at least widely collected. So there's great potential to sort of do something with this. I'll just show you a few images of one of our first attempts in working with this data, which is basically a multi-view visualization. So it's a number of coordinated linked views. Many of you have probably seen strategies like this before, but we've done some interesting tweaks to make it work with this data. So there's sort of a standard, you can select data and pull out subsets of it. There's a couple interesting things we do here. Even when we pull out this subset, we actually smartly extend the selection, both forward and backward in time. So we look for key points in the data, like a discontinuity in the force, where you may have picked up a block or put down a block, and we extend out to those points. Okay, the reason for that is that once you have this selection, and you want to, say, pull up a video based on this subset of data, you need the surrounding context in order to understand it. Okay? So I think I have that in the next video. This, by the way, is a plot of the left grasp force by the right grasp force. And it turns out that this region, sort of in the middle where you see a transition, those correspond to when you're handing a block off from one hand to the other, and the force changes in that way. So very quickly, actually, you can just select a portion of the data set that just corresponds to those block transfers. And I think that's what we see happening here. So we select just the block transfers. It gives us those points of the data plus a little bit of surrounding context. And you can see the video now is just sort of playing right through only those transfers. Okay, there's a couple of other interesting things that are going on here. So it turns out one of the quantities that's most interesting to these surgeons is the forces. Okay, so if you're looking, if you're like a mentoring surgeon looking at your trainee, you can't really see force. Okay, you can see some other things that you might be able to give them some tips to correct, but it's very difficult to sort of see force that's being applied until it's too late and you've just crushed a tissue or something like that. Okay, so force is actually one of the quantities that they're most excited about, and they really have no idea sort of what the right pattern of using force is. I mean, maybe that's a little too strong. They don't have, they see a lot of variation in force, especially comparing novices to experts, but it's difficult to sort of define an exact pattern to sort of teach people. So actually one of the most important aspects of the visualization from this user's point of view is overlaying these force plots onto the video. So with that, we can really see the force applied by each tool, and working with them, we put some thresholds in here, and we've even put a little sound in, some horrific beeping noises if you go beyond the threshold. But this, it makes something visible that wasn't before. And so it really sparks a lot of thinking about how visualization could be used in this environment. And some of our discussions because of this have now turned to, okay, could we make sort of a real-time heads-up display for surgeons? So then this sort of data analysis after the fact almost becomes a way of prototyping tools that could also be used live during surgery. Okay, so they're thinking a lot about force, they're thinking about trajectory, and they probably posed 3 or 4 questions that we felt the visualization could help them answer, but then we also found a few things that were surprises that we hadn't never thought of before. One is kind of interesting. I'm not really sure what this means, but if you look at the force plots over time, we found across many of the examples that there's this, what we've been calling a sympathetic grasp and release. Okay. So if you look at the plots over time, at the point where there's a grasp in one hand, there's quite often a sort of a release of pressure in the other hand, even when they're not sort of touching each other. And so you sort of grasp here and you pick up here. And we think that there's probably just some hard wiring in our brains to do this sort of thing. I don't know. Another hypothesis was that it's sort of a part of what surgeons try to learn in terms of respect for tissue. So if they're holding on to a single piece of tissue and they kind of push a little bit harder with one hand, they want to let up with the other so they're not tearing, and so that this just becomes sort of a skill that they learn. But this was a real surprise. Nobody had imagined that this was in the data, and we're not really sure if it's an interesting finding and sort of something that should be trained in terms of respect for tissue, or just sort of something that happens when we work with our hands naturally. So new insights raise new questions, I guess. Okay, one of the other things we're thinking about here is perceptual issues. So how do you display spatially complex motions? And again, here's some trajectories from the surgery, but this work is also relevant to the biomechanical analysis. We're working with pretty complex spatial patterns. And so you start thinking, and this is sort of the first attempt, we've got some shadows and things like that, but this, even with this display, you're not really getting a full sense of a really easy reading of the three-dimensional structure here. We do a lot more with realistic lighting, really indicating a very clear direction for the light source and so on. But there might also be different 3D forms we should look at as well. And then the other thing you notice here is as you're looking at this as a visualization, there's a lot of things that are changing. Okay, so you've got sort of this animated view, but you also have control over the camera. There's a lot of parameters you can sort of do interactively. And so what's the best mapping from user input into these 3D spaces? That's a very interesting question. Of course, the problem gets much more complex when we start to not just show 3D paths, but also then try to map data onto them. So here's a multivariate visualization that was inspired by Colin Ware's tracks of whales swimming through the ocean. This uses very similar mapping to encode grasp force and speed and passage of time in a three-dimensional picture. But this gets very complex because now you've got sort of a 3D shape that's changing its width. Of course, that visual cue conflicts with depth cue of something changing size and depth. So there's some interesting perceptual issues here when you start talking about mapping 3D data into these spaces. So one thing we've been doing to explore these issues is to kind of take a look at some of the fundamental design decisions you have in showing motion data that fundamentally represent motion. So we took a look at some of our examples like this chewing pig, thinking of the vertebra, the spine, and how they relate to each other. Even this motion of the duck, which I haven't talked about today, but a really interesting sort of chain of mechanical events that opens that duck bill. And we sort of abstracted these shapes, which all have some sort of important feature points that you might track in space, and also have a three-dimensional context, to a couple flying saucers with bumps on them. And made sort of a synthetic data set like this, which then we could animate in a way that's algorithmically generated. And then we looked at a number of different visualization options for depicting these. So the way we structured that actually was with a matrix like this, where we said, look, you have two dimensions that are really important in this data, the time and the space. And for each of those, three of the most fundamental decisions you have to make in creating a visualization is, do you control this interactively? Does it sort of go automatically or in an animated fashion? Or do you have sort of static presentation? And you can look at those sort of intersecting here. So for example, you might say, look, I really want to control the time dimension interactively, like scrubbing through time. But if I then am also supposed to control sort of the camera in order to get like a better perspective view of the scene, now I've got like multiple things to control, and this actually may be slower to analyze than if we use sort of an automatic camera rocking. Maybe we should even look at, go back to Murray and Muybridge and think about stroboscopic photography. That's sort of what's inspired some of these static choices as representing, providing a good representation for space. Okay, and so I won't go through this study in too much detail here, but I just want to give you a sense of some of the different visualizations we devised for this. I mean, this all takes place in a head-tracked stereoscopic environment. And there's different options, like how you control time and either interactively here, time may be animated. You always have head tracking, so you can sort of walk or move your head in and out of the scene to view it. Sometimes there's additional widgets placed here, which give you a better sense of space in the sense that you can kind of see perspectives of the scene as pictured from behind the object, even without rotating the scene to look behind. Okay. And we looked at this sort of for the synthetic data set I mentioned, and then also for some of the applications we've been studying, like the spine. Okay, so we actually ran sort of a user study to evaluate this, and I won't go through all the data because I want to go sort of broad rather than deep in this talk, but I think the most interesting finding to me was that this control over the time dimension appears to be very, very critical. I mean, even to the point where it's more important than the space dimension, right? So I think there's better alternatives, at least in what we explored, for looking at space either in a static presentation with some additional visualization widgets to help you understand space, or automatically animated, but that time you really want to be able to have interactive control over. So that, I think, will actually form a lot of the visualizations we create from here on out. And one of the reasons why we're interested in it is because as we look now towards scaling up to looking at many, many motions, okay, our displays are going to become much more complex. And I don't think it's going to be an option that we can just sort of interactively control everything. Right? We're going to need to learn sort of what's most critical. So this is one of the things we've been doing to inform that. Okay, so I want to talk about a few more areas of our work, but here's a couple of conclusions from this thrust of visualizing motion. I phrase these kind of as future work. So I think these are a couple of things that are most important for us to do. So one is really to have systematic studies of visualization design decisions. So we start talking about motion visualization, and there's a lot of literature on motion perception, for example, but it's very low level. We start saying, well, how much of that can we sort of transfer into visualizing biomechanics, or something which is inherently motion, okay, but where it's not just like a dot blinking on a screen. It really is like a pretty complex spatial motion. So I think we need a more systematic study of that. When we get to the point of creating applications, I think it's very important that we have some new visual abstractions. Okay, so we need to know how to represent variance and uncertainty. I know this is something you guys are really thinking about, but it's super important as applied to motion, right? Because that's, I think, what allows us to scale from this like single picture to really looking at a collection, which is what scientists really need. Okay, what we've started to work toward is methods that balance automated data analysis with visual data analysis to sort of combine the best of both worlds. I think that's really important, and methods that treat visualization as a process, not just a picture. So that's where we start getting into some of these interactive techniques, and that's actually what I want to talk about next. Okay. So a lot of this is sort of switching gears a little bit, but I want to talk a little bit about interfaces specifically for visualizations. And many of the problems that interest us are 3D, and just like these motions that exist in 3D space. But consider other things like, brain imaging, or fluid flows, or anatomy. All these are really 3D problems. Okay. So what are some of the challenges in interacting with these? Well, one is something as simple as selection. How do you accurately select for a volume of interest in one of these visualizations? Actually, it's pretty hard. How do you navigate through them? How do you do sort of overview and detailed visualization in these spaces? Okay, so here's some work we've been doing in this area. It's motivated actually by a new type of display. So we've constructed a visualization environment that looks like the schematic, where you have sort of a three-dimensional view, stereoscopic head track view on this vertical screen. And then you have a 2D table, which is a multi-touch table. One of the neat things this allows you to do is you can display things in your near space. So you can have a 3D model that appears to kind of float out in the air in front of or on top of the table. And then you get this very interesting effect where you're sort of looking at a 3D object, and you're able to interact just below it on the table's surface. So one thing we do with that is we use sort of an interactive shadow. And there's turns out actually if you sort of look at perceptual literature and human-computer interaction literature, there are many things actually which 2D controls can really help you do a 3D task. And so we think actually this could be a very nice way for working with 3D data, despite the fact that you've got sort of a 2D surface as your input. In fact, it's really a high-dimensional 2D surface because you can use many points of contact. Okay, that was a very simple example. Let me show you one way we scale this up for more complex visualizations. So this uses a technique called a world in miniature metaphor. And you might get to see it if my computer doesn't blow up. Okay. What we're doing here is thinking of, this is probably how often in these immersive environments you kind of scale yourself into this environment. It fills your whole context, which is what makes the immersion so great, but then you really can lose sight of where you are. So the metaphor we use here is that you have a miniature version of the world that floats above that table. It really is kind of in your near space, and you interact with that. Okay. And as you do your interaction here, you're affecting a more detailed visualization of the world behind. Okay, so here's what it looks like with data. This is looking at the visible human data set and the heart that's been extracted from it. And so we interact in this space. We use essentially a shadow, but we've augmented here by actually showing data from a slicing plane through that volume data on the table surface. Something which many of these medical imaging users are used to looking at anyway. So now you have this 2D input. You can interact here and it controls its mirror space. But as you manipulate that world in miniature, it changes the view behind. Okay. This is all head track, so as the user moves around, his perspective is changing. That's why it looks like the image is shaking a little bit. And now you can see how it sort of slices in. So his interaction is basically to move the slicing plane through the world in miniature. And he can navigate using the image data and this 3D miniature world to some place of interest, cavity he wants to see or something. And then the detailed view of that world shows up behind. Okay, so there's a whole series of 2D gestures to interact with this. Then we can start doing things to be able to query the data. So here's an example of drawing a path through the data. Okay, it's using a technique called balloon positioning, something Steve Finer's group developed, where you place a point in space and you sort of get its XY positioning based on the movement of a single finger on the table. Then to adjust the height, you move the other hand out from it. So the metaphor is like there's a balloon stuck with a string stuck between your two fingers, and then it floats up into the sky, and you kind of keep adjusting the slack on that balloon. It actually is a very controlled, precise way to position 3D points in space, which is something which is difficult to do if you just took a 3D wand or some virtual reality device. So again, I think there's actually somewhat counterintuitively a real advantage to working with this 2D space with 3D problems. Okay. Chris, are we going till 1? Or, okay. All right, I'm going to skip over a couple of these other things. There's some selection. I'm really interested in selecting 3D volumes. I think that's a real tricky piece of user interaction. But let me give you some sort of closing thoughts on user interfaces. So, one thing I hope I've been able to demonstrate, and I hope you guys can think about, is that interaction techniques in the context of scientific visualization are really different. Okay? So when we take selection, this is something that's been studied by the human-computer interaction community for decades. But if I say you have you select the neural fiber tracks in a brain, they're not going to have a solution. And so I think we need sort of a new trajectory of work that sort of really looks at how these things intersect, where you have sort of a visual that's been designed together with the interaction. You're thinking about these tasks in tandem. Okay. And I think some other things that are really important, we're actually very excited about this hardware that I showed you with the 3D display coupled with the 2D. And one of the problems you have in these traditional immersive environments, particularly you take like a cave or a large virtual reality display, you walk into them and you leave everything else behind. I mean, typically you have to also put on shutter glasses. So it's like you walk into a dark room, you put on sunglasses, and you've got nothing. Okay, you don't have your desk, you don't have your papers, you have nothing to do sort of real work. And so, so I think there's a chance now with new developments in hardware and so forth to really mix and match different display configurations. We say, I want the best of the 3D world that tracks stereoscopic view. But frankly, that 3D view isn't enough. I need to get my 2D plots. I need to be able to organize different data sets. I need to do all these sort of work things. Okay, and that's where this, for example, the multi-touch table can really come into play. We've seen some evidence that really helps you to sort of get beyond the picture to the point where you do work. You say, here's a plot. I want to export this line and do my statistical analysis on it, and so forth. So I think there's a real opportunity to do something with new hardware. Okay, and I want to close by talking a little bit about the connection between science and art. This is something is close to my heart as an artist and a scientist. And And I think there's actually some really great visualization research problems in this area. So I want to motivate this a bit by going back to some work that I did long ago as a graduate student. And Mike Kirby probably helped out with some of this work too. Thinking about how do you collaborate with artists. So here's an example of an illustration. Okay, it was created using colored pencil, and an illustration student drew this. And the challenge posed to her was, take this fluid flow data set, which flow past a cylinder. Here's a bunch of different quantities that have been calculated for it. How would you depict all this in a single image? And she came up with this mapping, and I can argue about whether it's a great mapping or not, but it's a very creative mapping. Okay. It reinterprets flow lines as vines, which change the thickness and have curls coming off them, and all sorts of other things. So I really like this idea that there's creativity and insight, visual insight, out there among artists and illustrators and graphic designers. And I think we very rarely actually are able to leverage that in scientific visualization. So how do we take more advantage of that? And we've done some work on 3D sketching as well to sort of enable that as part of my dissertation. But the takeaways are basically like artists that have this exciting visual insight, they should be able to contribute, but they can draw some concept sketches like this, but it's very hard to sort of go beyond that. So what we need is creative, iterative visual design and visualization. And when I give a visualization problem to my students, it's usually a month of programming, and then we come back with the first visualization. I really want to move away from that. I think we need iterative design up front. That's sort of low cost, and you can throw it away if you want, start over. And then we come to finally to a visualization. So how do we support that kind of a process, which is what everybody does in architecture and any other sort of visually dominated discipline? Okay, so one problem we looked at was this flow-inspired one. Okay, so pretty simple 2D flow. Just, even for something like this, an illustrator actually has some insight about how to depict this. This visual design decisions they make really make some sense. But can we create a tool to enable that type of process? Okay. So we actually developed a pen and tablet based streamlined visualization tool, essentially. And it draws upon research in pen-based computing. So let me just show you some of the gestures we used here. Our underpainting, if you will, is a line integral convolution of the flow. And if you want to create a new streamline, you just draw on top of that. Okay. And notice as you draw, or right after you draw, that mark that you made settles into a streamline which is actually accurate with respect to the underlying flow field. Okay. Okay, well, how would somebody actually work with this? How would like an artist or an illustrator work with this? Okay. So what if you say, oh, my line's not right, I want to extend it. Okay. So you do that sort of thing. Oh, this isn't going quite the right direction. Well, in a pen and ink illustration, I would redraw that. This is a little bit harder to do in pen and ink. But you can crop lines, you can delete lines. This is a ubiquitous scribble it out gesture. Okay. And so what this gives you is just this ability to just work very fluidly, no pun intended, with the fluid data set. And there's some interesting mathematics that go on behind this. So we have a similarity metric to sort of enable that ink data settling routine, which I think is actually critical. You need sort of that visual animation of the lines settling to sort of get this fluid process. And then we do some other things too, like say, look, we don't want to completely get rid of the computer here. We want the computer to do some things intelligently. So we've got a more gesture, which basically says, analyze what I've just drawn recently. You give me more of that. Okay, give me more in this visual style. You can actually say, no, I didn't like what you gave me, and back up a little bit and keep going. So it gives you this nice way to sort of explore the space. Okay. So we're combining here artist-driven, intense, sort of an illustrator's insight with the scientific data. And this is sort of a very first attempt at this that's pretty simple line drawing, essentially. But I think this concept is actually really, really powerful. You say, look, I want to have some ability to experiment, think quickly, work very immediately, as you would with pen and charcoal. But I don't want to just do that blindly. I want to have the data play a role in that investigation as well. And so I think this is actually the really interesting type of tool. Imagine if this could be linked up into VTK and you start sort of sketching out visualization designs with all sorts of algorithms and data underlying them as well. So I think the idea here is quite powerful, actually. We've done a little experimenting with it. You can see just, imagine you're a scientist sort of trying to explain this data to someone else even. You can emphasize parts and de-emphasize others if you like. Here's some other vector fields to illustrate. And it works for people who don't know how to program. We actually had the president of Minneapolis College of Art and Design, a couple of his instructors over, and first of all, they went into our lab and said, oh, this looks very foreign. Then they saw the tablet and they said, aha! This is what all our students have on their desks. So this is an interface that's really approachable to people who are outside of the computer science discipline. And of course, one of the interesting things I think is that if you start exploring these types of fluid interfaces with some of these visual designers, then the people who, the mechanical engineers say, well, wait a minute, we want that too. So I think there's actually a real opportunity here, even in connecting up with artists and so forth, to have the insights you generate from that feedback into the tools you use with the core domain scientists. These are what artists look like, in case you haven't seen it. No, actually, this was fantastic. This is a grad level graphic design lab that the students designed themselves at the Minneapolis College of Art and Design. And, these are some students from my class went over there to see it. So it's a different way of working. There's a lot of sort of visual ideation, quick work, sort of broad exploration. That's actually very different than sort of the linear path we often take in computer science. And I think if we can get more of that into our visualization tools, it's actually really going to help. For our motion project, one of those graphic designers, in the first week she was working with us, generated more than 100 visualization design ideas. I mean, she gave me a stack of 100 PDF files. Okay. Now, she just mocked these up in Adobe Illustrator. Okay, so it wasn't like this huge deal, but she generated 100 in a week. And I turned to my grad student who had been working on the project and said, how many iterations of visual design do you think we did all last semester? And he said 10, and I was like, no, it's more like 3. But it's just a very different way of working. Okay, so how can we capture this? So these are all different ideas related to the helical axis stuff I was showing you before, and we implemented some of them in this video we created. This was a neck circumduction exercise. Same idea as the helical axis I was showing you before, but here in human patients. And if you look at that instantaneous axis over time, it flies all over the place for something like this. How do you depict that? So a few visual iterations of design that you see here, and these were all inspired. I mean, just think about it. What's the use of transparency? What's the use of texture, color? Even those very, very simple things have a dramatic implications for how we read the visual. Okay. But typically, I think we just don't spend enough time kind of thinking about those ideas. So we created some tools that allow the graphic designer working with us even to just flip through different textures applied to this surface. Okay? And just the ability to do that, I mean, it's like tip of the iceberg, was dramatic because all of a sudden she could then throw in her 100 textures onto this and sort of examine, well, which ones are best? Which are best in different situations? So by the way here, the hypothesis of the orthopedics is that when you see the surface fold onto itself, that actually correlates with the spot where the patient exhibits pain. And so the current hypothesis is that if they can understand those, then they can really pinpoint treatments. And so if you could show a surgeon or a therapist a view that really highlights where those areas are, then all of a sudden they could use this more complex data in their treatment. Whereas right now, basically what they're doing is say, bend as far forward as you can, bend as far back. They get 2 numbers out and base all their treatment options based on that. So I think this is really exciting. You know, we had, this is like my plug here, illustrative visualization, but now with illustrators. And we had on campus, 30 years ago, there was a big football stadium, which then got demolished and they built the Metrodome. But the name of that area of campus still remained Stadium Village, even for all the years when there was no stadium. So about 2 years ago, we had a new stadium built on campus, and they put up a huge billboard saying, Stadium Village, now with stadium. You know? And I think that's kind of how I feel about illustrative visualization. We've learned so much from the arts and from the illustrators over the years in visualization. And we have all these non-photorealistic rendering techniques. We're drawing upon these traditions regularly. But it's very rare, actually, that you can get real living illustrators into the loop. So how do we create the tools to sort of enable that? It could actually be really powerful. Okay. Okay, so sort of summing up, I tried to show you today sort of 3 of the main research thrusts that we're working on. You know, visualizing motion. We have a lot of activity in that right now. Thinking about user interfaces, particularly in 3 dimensions, and how those are really unique for visualizations. So what are the unique problems when you start talking about interacting with data? And then how do you sort of combine science and art, but really thinking from the standpoint of like mimicking that drawing. Like how do we get something as immediate as that? How do those then translate into tools that can allow, you know, artists, illustrators to get involved in visualization as well? And I think all these things really are at this intersection. Okay. You can't separate the picturing from the interacting. They're there together. And so I think that's kind of what we need to be studying. Like how do those things work together? I want to acknowledge my students, super students who worked on this, and of course many collaborators in other domains who helped us with data and sort of framing a lot of these problems, and some of the support we've had. And thank you guys so much for inviting me. I really been enjoying it.
Maybe time for a question or 2 before we move on. Any questions for Daniel? Bob?
Dan, you know that Pythagoras in 600 BC was the first person I know of at least that visualized music and what you see. He showed people what music looked like and sounded like.
Yeah.
That's what Pythagoras did in 600 BC.
Yeah.
So you're in an honorable tradition.
As long as I'm in an honorable tradition, too. No, making things visible that you can't see. I mean, it reminds me of talking with horses with these surgeons. And I mean, to be quite honest, none of the techniques we're using in that visualization are super groundbreaking. But it's you put it in the hands of these surgeons, and they say, "Wow, you know, I haven't been able to see force before, and this radically changes everything." And I think a lot of our projects have kind of this ramp up where here's a tool that you know helps you with something immediately. And, oh, that's interesting. But, you know, it's not really what I'm after. I'm really after this, and we sort of have this back and forth collaborative discussion. And I think the next directions for the project are just so exciting. But a lot of it was spurred by giving them the ability to see force that they hadn't had. It was invisible to them. Wow, this is powerful if we can see force. And then it opens your eye. Oh, what else can we do?
It looked like you were trained as an artist, or you showed some images using the hand.
Yeah.
That was some of your direction. It's a radically different process, as you kind of indicated at the end, and how to think about problem solving and work through a particular methodology.
Yeah.
And versus a scientific methodology. And so how in your own work, you showed some great examples of the tools, but then how in your own work is the aesthetic, the approach that's coming from one art design informing or challenging some of the scientific or vice versa?
Oh yeah, great question. I guess I have a hard time separating them because I do training as an artist and I think of myself as an artist, but also you guys have been through years and years of PhD and everything else, and so you've got a lot of training together. And for me, the visualization really is right home because it gives you the ability to sort of do something creative visually you can't do any other way, but then also have this really strong technical component and scientific component driving it. So I love that combination. I think it's really hard to separate them. So like almost every project I do, I try to really think of the visual, really spend time kind of thinking about how would you refine the vision? How do you use color and form and narrative and metaphor and texture and all these things almost as an artist would approach it or a graphic designer, but thinking of it from the standpoint of the scientific process behind it. And so I guess that's the mental approach I take. I mean, in terms of like specific steps, we have critiques in my lab. And so we have like huge bulletin boards, and we put stuff up on the wall, and we learn to sort of discuss it as you would in our studio class. And that's something you have to kind of get used to if you haven't trained in that way. The other thing we do is we collaborate. So we work with people who are really, excellent, really trained solidly in like graphic design. And they come in and they do something like generate 100 images in a week. And the computer science students, their jaw just drops. It's, wow, And I think when you get these groups together and they start working together, there's a real respect that develops for the trade of the other group, and it makes you sort of want to learn a little piece of each other's workflow. And so, so my students, I see them now adopting some of the strategies that the graphic designer who's been working with us most does, where they'll mock things up first, and we'll go through more iterative design, whereas before it was sort of program, and then you come back and you got one variable mapped to red, one mapped to green, one mapped to blue, and you look at it and say, well, this doesn't work at all. But then to refine that is another month of program, and so, I think in our own workflows we need to, I think it would help us a lot if we are aware of that approach and try to incorporate it, as sort of a general statement. Then I also think there's a very interesting sort of research direction into like, hey, can we really make this a priority and sort of embrace it in our tools? And that could just make things so much more accessible to a broader range of people.
All right, we need to get Dan to lunch, as now that he's watched us eat our lunch. So let's thank Dan for a great talk.
Thank you.